thing.
Which side did you see me on?
Great.
Yeah, I went over there and I was like, okay, there's got this part on
Over there? Yeah. I was coming back this way.
Okay.
And I managed to hit one of the spots there. It's like one of the modern, someone's, you see it back now.
Yeah.
So it's 4 o'clock, so I'm going to get started. Okay. So here's what I'm going to be doing today. Again, I'm going over the agenda at the beginning, as usual. I did do Money's Point cards last class, so I do have a Money's Point to go over after that. And then I'm going to move sort of to where I left off last class. Last class, I almost but didn't quite finish 8.1.1. So I'm going to finish that off last class with one example I didn't do last class and do this class. Move on to section 8.2, do this stuff, which is a word problems, and then start the stuff from chapter 9. Again, I'm not going to have a chance, because of a couple of delays that happened last week, I'm not going to have a chance to finish chapter 9 today. I'll be finishing it on Thursday's class. I'm going to start review on Thursday's class, finish review on Friday's class.
So chapter 9 last.
The very last thing, exactly. So again, there's like 2 sections of chapter 7, 2 from chapter 8, 2 from chapter 9 that I covered. And again, I'm sort of covering each of them briefly, just sort of the essential topics. I'm trying to not do any of the, you know, the more advanced stuff. Yeah. And again, just for anyone who wasn't here on Friday, there is another written assignment that I handed out in class on Friday. It's also available on the course webpage. It's due this Friday, so by midnight, whenever you can get it done. What else am I going to say? Oh yeah, and I created a new web assign today. The last web assign is going to be due on Sunday at the end of the week. So, yeah, it's the one with, exactly, it's that one with the hiker and stuff. And the due date on the top is wrong. Yeah. Okay. So, one thing, I'm going to do this now because otherwise I'm going to forget. So the exam is on April 25th, which is a Friday. And I'm basically going to have office hours one day the week before that, so that hopefully if folks have any questions about stuff that's on the exam, they can come and ask me. And so I just want to determine sort of when we're going to have those office hours. So either it'll be on Tuesday, April 22nd, or Thursday, April 24th. And let's say, I'm trying to think what actually, you know, I'm going to give 3 options. 10 to 12, 12 to 2, or 2 to 4, 10 to 12, 12 to 2, or 2 to 4. Basically, I want to schedule my office hours such that those who have exams on those days can still attend office hours if they have questions. So I want to make sure, and again, I'm only going to come to campus, you know, one of those 6 times, so I'm just going to check of those 6 times which works the best for people with regards to when their other exams are and such. If you don't know when your other exams are, you can take a couple minutes to look that up. If you've got like a smartphone or something else, you can look up exams on. And so actually, maybe I will, yeah. I'm trying to think if I should do this now. Yeah, I guess I'll do it now, but if you want to take a couple minutes just to look things up, check your exam schedules, check which of these times work and which ones don't. And then like in a minute or 2, I'll take a vote on this to see which time works best for people. So yeah, just take a couple minutes to look that up. Yeah.
Oh, Thursday, Friday.
Do you have the handouts from last week at all?
I think so. Oh yes.
Yeah,
Does anyone see? I think they should be in here.
Those are the center problems, basically.
Okay.
That was at the end of 7 point something, on how to build the triangles into that. And then this we started 8, which is I reckon it's actually more than, like, you guys just like two.
I can't find.
Two different creators. You just solve one for X and plug them together.
Okay.
Remember that stuff?
Yeah, I think so.
I can't find them here, sadly, so they're probably in my office. But so how many people? Okay, so I'm going to hold the vote now. So how many people would like to be in office hours on Tuesday, April 22nd, from 10 to 12? Again, you can vote for more than one time if there's more than one that works for you. I want to figure out what works the best. So I see only one hand for this time. How about 12 to 2 on that Tuesday? 1, 2, 3, 4. Sorry, if we put your hands up again, because that's 1, 2, 3, 4, 5, 6. How about 2 to 4 on that Tuesday? 1, 2, 3, 4. Okay. How about 10 to 12 on the Thursday? I see 1. How about 12 to 2 on the Thursday? 1, 2, 3, 4, 5, 6, 7, 8. 9. How about 2 to 4 on the Thursday? I just see 1. Okay, so this will be, I'll come in on 12 to 2 on that Thursday, the 24th. So that'll be the day before the exam. And if you want to ask me questions in person, that's the time to do it. Obviously, you can send me emails whenever, and I will try to answer those emails. I will actually be out of town the week before Easter. That's the week before this. I will be out of town, but starting that Monday, I'll be back. So, yeah. Okay. So that's what my office hours are going to be. So now I'm going to move on to talking about the muddiest point. And again, one of the things I spent a fair bit of time on Friday's class was talking about word problems that use law of sines and law of cosines. And so I got 2 different muddiest point cards asking for me to do another word problem as an example. So this is the one I'm going to do. I picked it from the page 498 of the textbook, number 22. One thing to mention is that some of the ones from the textbook, some of the examples I did last class are harder than anything you're going to see on the exam. This is sort of the difficulty that you would see on the exam. Again, the reason I did some harder examples was to help you out with the written assignment. But yeah, if you think about exam difficulty problem, this is about the difficulty you would see on the exam in terms of a word problem. So here we have a triangular plot of land. One side is 420 feet, another side is 350, and the third is 180. And we want to approximate the smallest angle between the two sides. Now, one thing to mention about a triangle is that the biggest angle is always opposite the biggest side, the smallest angle is always opposite the smallest side. So that would be the smallest angle there that we're trying to find, that alpha. And so I'll call that side A, that side B, and that side C. Now this is a side situation. We know 3 sides of the triangle. In that situation, we can always solve the triangle using the law of cosines. So the law of cosines says, and we're going to use the law of cosines with this angle alpha in it. So it's going to be the one, because that angle is the angle we're looking for, so it's going to look like a squared equals b squared plus c squared minus 2bc cosine alpha. So a is 180, b is 420, c is 350, b is 420, c is 350 cosine alpha. And so we pull out a calculator. $180 squared, 32400, 420 squared, 176,400, 350 squared, 122,500, 2 times 420 times 350, 294,000 cosine alpha. So I'm going to move this thing with the cosine alpha over to the left, the 32,400 over to the right. And so we'll get 294,000 cosine alpha equals, so 176,400 plus 122,500 minus 32400 equals 266,500. So then I divide this by 294,000. .906. So I got that cosine alpha is 0.906. So if I want to find what alpha is, I just do cosine inverse of that. So cos inverse 0.906 is 25 degrees. So here I would say the smallest angle is 25 degrees. Any questions about how I did this one?
Would it matter which angle you pick?
If we pick this one, this would not be the smallest angle. This would not be the smallest angle. So yes, it does matter which angle you picked. And you pick the one that, so remember, it was this angle, these things would be rearranged in the formula.
Yeah.
Because if it was this angle, we use one or the other, so we get a different answer.
Okay.
So if we want to find the smallest angle, the thing to remember is the smallest angle is always opposite the smallest side. The biggest angle is always opposite the biggest side. And that's just sort of visually, that's true. Yeah, exactly. Small angles will have a small thing across from it. Okay. So any questions before I move on to where I left off in Chapter 8 last class? Great. So Chapter 8, I was talking about solving systems of equations by substitution. And I did a bunch of examples, and the one example I didn't do was example 4. So this is sort of where I left off. I did example 2, I did example 3. I'm going to move on to example 4 from section 8.1. So the first thing to mention, this is what's called a system of equations. There's two different equations with two different variables in each, two different what are called unknowns. We're going to try to solve the system of equations, try to figure out what x is and what y is. Now the method we're using right now is this method called substitution, which means first make sure one of the equations is rearranged so there's just one variable on one side, and then plug that equation into the other equation. So the first equation is already rearranged that way. I already have y equals something. So now that means in the second equation I can replace the y here with the something. I don't know where that's coming from. So if y equals this, then we can replace the y with that. So we'll get 10 over x plus 3 equals negative x plus 8. And now this equation only has one variable in it, so we can solve it normally. So multiply both sides by x plus 3. Expand this thing, we get minus x squared plus 8x minus 3x plus 24. Then to keep solving that thing, I'm going to need to move everything onto one side and then factor. So move everything to the left, so I'll get x squared. 8x minus 3x is 5x. Move to the other side, I have minus 5x. 10 minus 24 is minus 14. So move everything to the left, I'll get x squared minus 5x minus 14 equals 0. So if I want to factor, I want two things that multiply to negative 14, add to negative 5. It turns out to be negative 7 and positive 2. So either x is 7 or x is negative 2. Now in each of these situations, we need to figure out what y is, right? So if x is 7, we need to figure out what y is. If x is negative 2, we need to figure out what y is. And we can do so using this equation. Y equals negative x plus 8. I could also use this equation if I wanted. Either one of them will tell you what y is. So if I use the second one, I'll have y is negative 7 plus 8. which is positive 1. So this solution is 7, 1, right? X is 7, y is 1. If x is negative 2, I'll have negative 2 plus 8. Negative 2 is 2. 2 plus 8 is 10. So this solution is negative 2, 10. X is negative 2, y is 10. And if you want to check, you can check those with this equation. This equation, if x is 7, y is 1, we have 1 equals 10 over 10. Yes, this one works. We check negative 2 and 10. 10 equals 10 over negative 2 plus 3. Negative 2 plus 3 is 1. 10 over 1 is 10. Great. So those two solutions work with both of these equations. Oh. That was supposed to be an or, I think. I don't know why it became an O for negative 210. Any questions about how example 4 worked here? So this is a method of substitution for solving systems of equations. I did a bunch of examples on Friday class. I did this example here. I'm sure you've all seen examples of this sort of idea before. In fact, I did some things like this at the beginning of the semester in this course. What's going to be new likely, or well, no, it's probably not new, but it's sort of more new, is the idea of solving systems of equations by this method that's called elimination. The method of elimination, for those who haven't heard of the name before, is what happens when you take two equations, you either add them to each other or subtract them from each other. So here's an example of a system of equations we can solve with elimination. How many people feel like they remember how to solve a system of equations like this? I see a couple people. How many people have done something like this before but don't remember how? Okay. How many people have never solved something like this before at all? Okay, there's a bunch of people in that camp too. It turns out that elimination is oftentimes a faster and easier method to work with than substitution, but it doesn't work in as many situations. It's not as general. So the method of elimination works in a very specific situation, which is where we have what are called linear systems of equations. A system of equations is linear if every term in every equation is just a constant times a single variable. So for example, this one's linear. It's a number times x minus a number times y equals a number. This one's linear. It's a number times x plus a number times y equals a number. Again, the numbers here are complicated. Here the number is 3 over 2. Here the number is square root of 2. Here the number is 54.2. Here the number is pi. But the key thing is they're all just numbers. There's no x squared in there. There's no square root of x in there. There's no x over y in there. There's no x times y in there. These are examples of equations which are not linear. Square root of x plus y squared is 22. It's not linear because you don't just have an x, you don't just have a number times x, you actually have a square root of x. Here we don't just have a number times y, we have y squared. Here we don't have a number times x or a number times y, we have x times y. That also makes it not linear. 1 over y, you're also not allowed to do. With 1 times y would be okay, but 1 over y is not linear. 12, again, 22 and the 12 aren't what are causing the problem. The square roots, the squares, multiplication, division, that's causing problems. So these sorts of equations are what are called linear equations. These sorts of equations are not linear equations. And again, this method of elimination that we're going to use only works with linear equations. It only works with equations where every term is either a number times x or a number times y. Even if those numbers are something complicated like 3 over 2 or square root of 2. Any questions about this idea of linear equations before I move on to talking about how to solve them? Okay. So, the method of elimination that we're going to use is going to try to take terms in each equation and cancel them with each other, either by adding the equations to each other or subtracting the equations from each other. So the method's going to work like this. We're going to look at the equations and we're going to multiply each equation by a number so that there's one variable in which both coefficients are the same. So for example, if there's a 3x in the first equation and a 2x in the second, we multiply the first one by 3 and the second one by 2. That'll make the 3x into a 6x and the 2x also into a 6x. So it'll make those two things the same. So maybe I should sort of explain that a little bit more on the board. So if I have like 3x plus something and 2x plus something, I'm going to multiply this one by 2 and this one by 3. Because when I do so, this will become a 6x in this one and a 6x in this one. We've made the two terms the same. Then we're going to either add one equation to the other or subtract one equation from the other. If it's like a positive 6x and a positive 6x, we're going to subtract the two equations. We're going to take this equation minus this equation, because 6x minus 6x will give you 0. If it was positive 6x and negative 6x, then we'd add the two to make them cancel. Once we do that, these two things will cancel each other out, which means that what's left will only have one variable in it, rather than two. So then that thing that's left can be solved. And solved for that one variable that's left. And then whatever you get from that can be plugged back into the original equation to find the other variable. Oh, there we go. So I want to give you an example of how this works. And the example is going to be example 5 here. Here we have 4x plus 5y equals 13. And 3x plus y is negative 4. So here we have a 5y and a y. And we want to make those two things the same. So we could make a y into a 5y just by multiplying this whole equation by 5. So if I multiply that whole equation by 5, the first one will just be 4x plus 5y equals 13. And the second one will become a 15x plus 5y equals negative 20. If I multiply the whole thing by 5, multiply this by 5, this by 5, and this by 5. I multiply every single thing by 5. And I get this. Now that these two things are the same, I'm going to take the first equation minus the second one. If I do 4x minus 15x, that gives you negative 11x. If I do 5y minus 5y, that gives you 0y. And 13 minus negative 20 is 33. So again, this 0y really isn't anything. So I really have the equation negative 11x is 33. So x turns out to be negative 3. And now that I found what x is, I can go back and plug it into the other two original equations to find y. The one I'm going to plug it into is the second one, 3x plus y is negative 4. But if you plugged it into the first one, it would still give you the same answer. So here I'll have 3 times negative 3 plus y is negative 4. 3 times negative 3 is negative 9. Add 9 to both sides, and I get that y equals 5. So the solution here is negative 3 comma 5, right? Oh, this is a y. It looks like an x, it's a y. X is negative 3, y is 5. That's what the solution is going to look like here. Any questions about how I did example 5? No? Again, so you want to multiply one or the other equation by a number to make one of the terms the same, to make them both be 5y, for example. Subtract one from another, or add one from another to make these two things cancel. Here I'm subtracting to make them cancel. Then I just have one variable left. I can solve for that variable, plug back into one of the original equations to solve for the other variable. This usually is faster than the method of elimination I did before. It's usually faster than trying to solve this first equation for y, or whatever. Yes?
So you could have done it for the x's as well, you just have to multiply both?
Yeah, you have to multiply this one by 3 and this one by 4. Yeah, and that would also have worked. Yeah, it was just taking a little bit more work. Yeah. Okay. The other thing to mention is that, again, I've shown sort of examples of systems of two, like before with substitution, where we had situations where we had no solutions, and situations where we had multiple solutions. With linear equations, we can have situations where there's no solutions to the equation, and there's situations where there's what are called infinitely many solutions. So what happens is if we get a false equation, like 1 equals 2 in the method of solving, then we know we have no solutions, because it's impossible for 1 to equal 2. If we get a true equation in solving, something like 1 equals 1, then we know there's going to be infinitely many solutions. Again, a true equation, like 1 equals 1, every single x is a solution to that equation. Every single x makes that equation true, which is why we say we have infinitely many solutions. When we want to sort of describe what those infinitely many solutions are, all we do is we sort of describe those using one of the two equations. Again, either of those equations on their own is an equation of a line. Like if you graphed 4x plus 5y equals 13, that would be a line. It turns out that all the solutions to that equation would be the points on that line. So, I'm going to do a couple examples to illustrate this idea. So example 6, I have 3p minus q is 7, and negative 12p plus 4q is 3. So let's say I want to make this 3p cancel the negative 12p. Well, I'm going to have to multiply that thing by 4, right? 3 times 4 will give you 12, which will cancel the negative 12. So I'm going to multiply that first equation by 4. Now, if I do so, I get 12p minus 4q equals 7 times 4 is 28. And the second one's going to be the same. And then I can add the two equations to each other. 12p plus negative 12p is 0. Negative 4q plus 4q is 0. 28 plus 3 is 31. So I have now the equation 0 equals 31. I can tell, since this equation is false, that there are no solutions. So again, if you do this sort of cancellation method, you get a false equation out of it, something 0 equals 31, there are no solutions. Yes?
How do you know when to subtract or add the equations?
If it's a 12 and a negative 12, then you add to cancel it. If it was a 12 and a positive 12, you subtract. Yeah. Yeah. Yeah, add if they're opposites of each other, subtract if they're the same. If that makes sense. Yeah. I mean, the other way you could do this is you can multiply the first one by negative 4 and then subtract the equation. If you multiply this by negative 4, you'd get a negative 12, and then you could subtract them. That would also work. It would also give you exactly the same answer, in fact. Yeah. So that was an example of a situation where I had no solutions. The next example is going to be a situation where we have infinitely many solutions. Example 7. Here we have x minus 5y is 2, and 3x minus 15y is 6. So here I'm going to take that first equation, I'm going to multiply it by 3, because then I can make an x and same thing as a 3x there. And I will get 3x minus 15y equals 6. And you'll notice the second equation is also 3x minus 15y is 6. You notice when I multiply that thing by 3, I got exactly the same thing as the second equation. And then if I subtract those two equations, 3x minus 3x is 0. 15y minus negative 15y is 0. 6 minus 6 is 0. So I get the equation 0 equals 0. Now this is a true equation. Right? This equation is true for every single value of x. What that means is that the solutions are all points on the line 3x minus 15y equals 6. Again, the solution, because these two equations were the same, basically these two equations, yeah, we basically only had one equation rather than two. And if we only had this one equation, 3x minus 15y equals 6, that one equation is a line. So the solutions to this linear equation are all the points on this line. On that, yeah. So basically, if you can multiply one equation by a number to make both equations the same, that thing that you get that's both the same, that is the set of solutions. It's a line. Sadly, I won't have time in this course to sort of talk about why the set of solutions is a line in this situation. All I'm really going to be able to tell you is that it is. But if you're interested in learning that, I can talk about it after class or something. But, yeah. Any questions about this example? Yeah, one thing I also want to mention is that if you look at the solutions in the back of your textbook for these sorts of problems, they will just write this thing, 3x minus 15y equals 6, as the answer in the back of the textbook. They might also write this thing, x minus 5y equals 2, as the answer in the back of the textbook. Those are two different ways of saying the same thing. But, yeah. Sorry? Oh, I didn't give you one of these on WebAssign because the WebAssign, yes, because I knew that the WebAssign would not mark these ones correctly. Like it would be too picky. I actually looked at the way the WebAssign answers were set up for this question. I was like, you know what, I'm not giving you these on WebAssign. But again, they could come up on the exam. So, yeah. And on the exam, again, this would be correct. This would be correct. If you solved it for like y equals mx plus b, that would also be correct. Okay. So the last thing I'm covering in Chapter 8 are word problems. And basically, these are going to be word problems that involve systems of equations. Word problems that require you to set up a set of two equations and to solve them. Again, the sets of equations are called systems. Sorry, I'm just realizing that some of the board's cut off in this video, so I'm pushing that back. There we go. Okay. So, I'm first going to go over a strategy for approaching these word problems, and then I'm sort of going to go through some examples. So again, the sort of the hard part about the word problems, the thing we haven't done before, is taking something that's given to you in words and turning it into equations. And so that's mostly what I'm going to be talking about here. So the first thing to do if you ever get a word problem is to summarize all the information in the problem, sort of make a little point form summary if you want, or just sort of think about it in your head. You don't necessarily have to, you don't have to write a quote form summary as part of your solution if you don't want to. But one thing to mention is if you try to start solving the problem before you've read it from start to finish, there's some really common mistakes you can make. So make sure you've read the problem from start to finish before you do anything else. Second step is to figure out what you are looking to find, basically. So the question asks, find the dimensions of a rectangle, then the things you're looking to find are the length of the rectangle and the width of the rectangle. If it asks, find how many passengers were on a jet plane, what you're looking to find is the number of passengers on the jet plane. The things you're looking to find are what you call x or what you call y. X's and y's should always represent what you are trying to find in these sorts of problems. They should not represent something that you already know. That's the key thing. Variables represent things you don't know. They're unknowns. Third step is to look at the piece of information we do know. And each piece of information we know should give you an equation. If we know one piece of information, that should give you an equation with x's and y's in it. If you know another piece of information, it should give you a second equation with x's and y's in it. We should always have the same number of equations as unknowns. So if there's two unknowns, there's an x and a y, there should be two equations. If we can't get two equations, there's some information that we've been forgetting about finding. And the fourth step is to, once we have those two equations, two unknowns, solve it. Figure out what the answer is. Last tip, interpret the answer in a sentence. Again, the answers to problems like this, I don't want you to say like x is 16 and y is 12. I want you to say the length of the rectangle is 16 and the width is 12. You know, tell me what you're actually saying when you're saying x is this and y is this. Any questions about these techniques before I move on to examples? Okay, I'm going to move on to examples. So, first one here is example 8. It says, find two numbers that have a sum of 10 and a product of 22. Well, because it says find two numbers, the unknowns are going to be the two numbers. So x is going to be number 1, y is going to be number 2. Right? So the first step, I read it. So I don't even need to summarize this, it's only one sentence. But second step, identify what are the unknowns. X is the first number, y is the second number. Third step, look for the piece of information that we are given. What we do know is that the sum is 10 and the product is 22. Sum represents that we're adding the numbers together. Product represents that we're multiplying the numbers together. Right, so those are the two equations. The sum is 10, means x plus y equals 10. The product is 22, means x times y equals 22. So now we need to solve that system of equations. The first thing to mention, this is not a linear system of equations because we have an x times y down here. So we're going to have to solve it by substitution. So first I'm going to rearrange this first one to get y equals 10 minus x. And then I can plug that into the second one. I'll get x times 10 minus x equals 22. So if I keep going, x times 10 minus x will be 10x minus x squared. Move everything to the right-hand side. I get 0 equals x squared minus 10x plus 22. I want two things that multiply to 22, add to negative 10. Wait a second, did I? Yeah, okay. Yeah, I'm going to need to, those two numbers are, we need a quadratic formula here. So this one doesn't factor. So if you get a quadratic equation that doesn't factor, you need a quadratic formula. Negative b is negative 10, which is positive 10. B squared is 100. A is 1. C is 22. So 4 times 22 is 88. 100 minus 88 is 12. 12 is really 4 times 3. So that becomes 2 square root 3 over 2. Ten divided by 2 is 5. 2 square root 3 divided by 2 is square root 3. So the two solutions are either 5 plus the square root of 3 or 5 minus the square root of 3. Now if x is this one, right, if x is 5 plus the square root of 3, then y is going to be 10 minus that thing. 10 minus 5 is 5, negative the square root of 3 is this. So if x is 5 plus the square root of 3, y is 5 minus the square root of 3. If x is 5 minus the square root of 3, oh boy, I need to move this down a little bit. Y, okay, I'm going to do it below. So if x is 5 minus the square root of 3, y is going to be 10 minus 5 minus the square root of 3. 10 minus 5 is 5, negative the square root of 3 is plus the square root of 3. So if x is this, y is this. If x is this, y is this. So clearly there's two different ways of giving you the same two numbers. 5 plus the square root of 3 and 5 minus the square root of 3. Either x is 5 plus and y is 5 minus, or x is 5 minus and y is 5 plus. So I can say the two numbers are 5 plus the square root of 3 and 5 minus the square root of 3. And likely if I was going to give this one on the exam, I would make it so that this thing actually could factor, and you wouldn't have to use the quadratic formula. Any questions about example 8 here? Okay. Now I'm going to move on to example 9, which is a little bit harder. Okay. Okay. So here we have a situation. A man rows a boat 500 feet upstream against a constant current in 10 minutes. He then rows 300 feet downstream with the same current in 5 minutes. So if he's going upstream, it's 500 feet in 10 minutes. And if he's going downstream, it's 300 feet and 5 minutes. Again, I've summarized the information in this question. It asks you to find the speed of the current and the rate at which the man can row in still water. So those are the two unknowns here. That what asking you to find is what's the speed of the current, what can he row in still water. So my x is going to be the speed of the current, and the y is, I'll call it the speed of rowing. Right, those are my two unknowns here. Those are two things I'm asked to find. What's the speed of the current? What speed can he row in still water? So then, I've got to come up with two equations involving these two unknowns. Now, the key thing to mention is these two unknowns are both talking about speed. So I'm going to try to translate this information into information about speed. And if I was going to give this to you on the exam, I'd give you sort of hint speed equals distance over time, just so you don't worry about not being able to do this because you don't know that formula from physics. So here, the speed, right, the distance is 500 feet and the time is 10 minutes. The speed is going to be 500 over 10, which is 50. Here, the speed is going to be 300 over 5. 300 over 5 turns out to be 60. Now, the key thing is if you're rowing upstream, the current's going to be slowing you down. So the speed you're going to go is going to be the speed of the rowing minus the speed of the current if you're going upstream. So if you're going upstream, speed equals rowing minus current. That means 50 equals y minus x. If you're going downstream, the current's going to help you. It's going to make you go faster. So the speed of the current's going to add to the speed of your rowing. So 60 is going to be y plus x. And you'll notice that these two, first thing that these are linear equations. There's no y squared, there's no y times x. It's just a variable with a number, a visible one in front, variable with a number in front. And the other thing to mention is that these two, you've got a negative x, and here you've got a positive x. So we can easily add these two equations, use elimination to solve them. And if we add the two equations, 50 plus 60 is 110. Y plus y is 2y. Negative x plus positive x is 0x. So this means 2y is 110. Divide both sides by 2. Y is 55. Now, if y is 55, we know we can use a second equation. 60 equals y plus x. So 60 is 55 plus x, which means that x, if we subtract 55 from both sides, is 5. So he can row at 55 feet per minute, and the current is 5 feet per minute. Right? The speed of the current is the x. The x is 5. The speed he can row is y. Y is 55. So we can row at 55 feet per minute. The current goes 5 feet per minute. I just realized this problem is kind of, the way I've done this is kind of S-shaped. I started here, then moved over here, then back across, and then like that. Yeah. Rather than sort of following nice columns or anything like that. We solve the problem in this roundabout form on the board. Any questions about example 9 here? Okay. If not, I'm going to move on to example 10. So example 10. So here we have a situation where a farmer's trying to come up with how to feed his livestock. And he's got 2 different feeds. He's got oats and he's got cornmeal. Oats have 4 grams of protein and 18 grams of carbs. Cornmeal is 3 grams of protein and 24 grams of carbs. And what he needs are 200 grams protein and 1320 grams carbs. All right, so this is my summary of the question. Now, the first question we ask after we summarize the question is, what are the unknowns? What are we being asked to find? And here it says, how much of each must a farmer feed his livestock? So what we're asking to find is how much oats, how much corn, right? So X is going to be the amount of oats. Y is going to be the amount of corn. Now, one thing to mention is the most common mistake I've seen students make in this sort of problem is to say X is the amount of protein, Y is the amount of carbs. The reason we know that's not the situation is because we know the amount of protein. We know the amount of carbs. And again, the X and Y always have to be things we don't know. We don't know the amount of oats. We don't know the amount of corn, even though we know the amount of protein and carbs. So what's going to happen next is we're going to set up equations. And again, the equations will come from the information we do know. So again, the oats and the corn is the information we don't know. The information we do know is the protein and the carbs. So there's going to be a protein equation, and there's going to be a carbs equation. And the protein equation is going to say the amount of protein is going to be the amount of protein in the oats plus the amount of protein in the corn. Right? If you have X ounces of oats and you have 4 grams of protein per ounce, the total amount of protein in those oats is going to be 4X. You have Y ounces of corn, you have 3 grams of protein per ounce, the total amount of protein in the corn is going to be 3Y. And the carbs equation is going to look like 1320 is 18X plus 24Y. The amount of protein, the amount of carbs total is going to be the amount of carbs in the oats plus the amount of carbs in the corn. Carbs in the oats is going to be the amount of carbs per ounce times the number of ounces of oats. The amount of carbs in the corn is the number of carbs per ounce times the number of ounces of corn. And so here's our two equations, and we're going to modify them so that they cancel each other. Now here we've got a 3 and a 24. If I multiply the 3 by 8, I'll be able to cancel off the 24. So this first equation, I'm going to multiply by 8. 200 will become 1600. 4 times 8 is 32. 3 times 8 is 24. The second equation I'm going to keep the same. And then I'm going to subtract the two equations. 1600 minus 1320 is 280. 32 minus 18 is 14. 24 minus 24 is 0. So 14x is 280. Divide both sides by 14, I get that x is 20. And now that I know that x is 20, I can use, let's say, this first equation to find y. So I use that first equation, and I get 200 equals 4 times 20 plus 3y. 4 times 20 is 80. 200 minus 80 is 120. Divide both sides by 3. Y is 40. So the answer is going to be that he must use 20 ounces of oats and 40 ounces of corn. Right? The amount of oats is 20 and the amount of corn is 40. Any questions about example 10 here? I want to mention that if there's a word problem like this on the final exam, about 40% of the marks for the question will be coming up with these two equations. There will be a fair, another 50% of the marks will be taking these two equations and getting these two numbers, and the last 10% of the marks will be writing the two numbers in a sentence. So usually you can get, even if you can't actually go through the process solving these equations, you can still get marks for these questions if you can come up with the equations. Because again, that's the part that's sort of new that we didn't do in, up here when we were just solving systems that I already gave to you. So again, if you're studying this for this sort of stuff, try to focus your studying on how do you come up with the equations. Any other questions about example 10? Okay, so I'm going to move on to start chapter 9. We'll see how far I get in chapter 9 today. Again, whatever I don't get to today, we'll cover in Thursday's class. And I'm just going to hand out the handouts for chapter 9 now. Chapter 9 is on what's called sequences and series. Again, this is something that's in the grade 12 curriculum, I believe. Yes. And will also come up again in Calculus 2. It doesn't come up again in Calculus 1, which is one of the reasons we always cover it really late in the course, and it's one of the things we cut off if we run out of time because it's not used again in Calculus 2, but it will come up in Calculus 2. So again, that's what we're talking about. We're talking about sequences and these things that are called series. So the first thing I'm going to talk about are sequences. And sequences are oftentimes written as something like this. We put these curly brackets and we put a formula inside the curly brackets. And if we have a formula inside curly brackets, we can do things like find the first 5 terms of that sequence. How many people here know how to find terms of a sequence using a formula like that? Do you remember sequences and formulas at all? How many people have done something like this before and they forget how to do it? How many people have never done stuff like this at all before? Okay, there's at least one. The key thing about this is, again, well, I should say, it turns out if you know what's going on, it's actually easy. If you're finding terms of a sequence, all you've got to do, the first term of the sequence comes from plugging in 1. The second term from plugging in 2. The third term from plugging in 3. Fourth term from plugging in 4. Fifth term from plugging in 5. So trying to find terms of a sequence, that's all that you need to do. So before I go on to examples like that, I'm going to talk about what a sequence is. A sequence is just an infinite list of numbers. Usually the numbers in the sequence form some sort of a pattern, but sometimes they don't. So the first one, 1, 2, 4, 8, 16, 32, right? That's a sequence where each thing is 2 times the number before. It's a sequence of powers of 2. This second sequence, can anyone tell me what the second sequence is? No one recognize it?
Pi.
It's the digits of pi. The second sequence is the digits of pi. Now the digits of pi, as you may know, do not actually follow a pattern. There's no way to predict the next digit only knowing the digits before. You need to actually know some more information about pi in order to predict what the sequence does. So it turns out that, yeah, this is an example of a sequence which there really isn't a pattern to it. There was a definition of it. It is the digits of pi. And there's a way of computing the next thing and the next thing and the next thing. But there's no, it doesn't repeat itself. It doesn't do any, sort of follow any pattern. And this last sequence is like square root of 1, square root of 2, square root of 3, square root of 4, square root of 5, square root of 6. Right? It's all the square roots, basically. But some of them, like square root of 1 is written as 1. Square root of 4 is written as 2, rather than a square root of 4. And so those are what sequences are. They're infinite lists of numbers. When we're talking about sequences, the numbers in the sequence are called terms in a sequence. The first term we call A1, second term we call A2, third term we call A3. So in this second sequence, A5 is 5. Let's say that the fifth term of the sequence, 1, 2, 3, 4, 5, is 5. A6 is 9. That's saying that the sixth term of the sequence, 1, 2, 3, 4, 5, 6, is 9. Any questions sort of about what sequences are, what I mean when I say terms of a sequence before I move on? So the key thing we're going to do in section 9.1 is to find terms of a sequence. And the easiest way to write down the pattern that you see in a sequence is through a formula. So for example, this sequence here, 1, 1/2, 1/3, 1/4, the pattern in this sequence is it's all the fractions 1 over a number. Right? This is 1 over 1, 1 over 2, 1 over 3, 1 over 4. So we can write it like this. an equals 1 over n. That means if you want to find the first term, a1, we do 1 over 1. If you want to find the second term, a2, we do 1 over 2. If you want to find the 10th term, a10, we do 1 over 10. We can also write it with these pointy brackets like this. If I say pointy brackets 1 over n, I'm saying that an is 1 over n. And we can use these formulas really easily to come up with a list of terms in a sequence. If you want to find the first term, you just plug in 1 into the formula. If you want to find the 16th term, you just plug in 16 into the formula. It's that simple. So example 1, I'm going to find the first 4 terms of the 8th term of each of these sequences. Example 1, great. So the first one, I have 10 plus 1 over n. That's the sequence. So if I want to find the first term, a1, I'm going to plug in 1 into that formula. 10 plus 1 over 1 is 11. If I want to find the second term, a2, I put in 10 plus 1 over 2. That's 10.5. If I want to find the third term, I do 10 plus 1 over 3. That's 31 over 3, if you write that as a fraction. If I want to find the fourth term, it's going to be 10 plus 1/4, which turns out to be 10.25. And it asks me to find the 8th term. That means I want to find A8. And I plug in 8 for n. So I have 10 plus 1 over 8. That's 10.125. Any questions about how I did example 1 there? Okay, example 2. The sequence is square root of 2. So if I want to find the first term, I've got to look in this formula and replace every n I see with square root of 2. Or with 1, sorry, replace it with 1. There are no n's, so I don't have to do anything. The first term is square root of 2. The second term, if I plug in 2, I still get square root of 2. Third term, if I plug in 3, sorry, I still get square root of 2. Again, there's no n's for me to plug in something for. The fourth term, also square root of 2. The eighth term, also square root of 2. So if there's no n's in something, it just means it doesn't change from term to term. Every single term of this sequence is the same thing. So this is the sequence square root of 2, square root of 2, square root of 2, square root of 2. That is a sequence. It's a list of infinite list of numbers. It's a silly sequence because it doesn't change, but it is an example of a sequence. Oh, sorry, this is still example 1. This is example 1b. Example 1c, we have negative 1 to the n plus 1 plus 0.1 to the n minus 1. So if we want to find a1, we're going to plug in 1 every time we see an n. So we have negative 1 to the 1 plus 1 plus 0.1 to the 1 minus 1. 1 plus 1 is 2. 1 minus 1 is 0. Negative 1 squared is 1. Anything to the 0 power is 1. So the first term in this sequence is 2. A1 here is 2. If we want to find the second term, we're going to do negative 1 to the 2 plus 1 plus 0.1 to the 2 minus 1. 2 plus 1 is 3. 2 minus 1 is 1. Negative 1 to the 3 is negative 1 times negative 1 times negative 1, which is negative 1. 0.1 to the 1 is just 0.1. Negative 1 plus 0.1 is negative 0.9. You can continue this pattern. A3 is going to be negative 1 to the 3 plus 1 plus 0.1 to the 3 minus 1. 3 plus 1 is 4. 3 minus 1 is 2. Negative 1 to the 4 turns out to be 1. This turns out to be 0.01. So we get 1.01. If we do A4, we're going to have negative 1 to the 4 plus 1 plus 0.1 to the 4 minus 1. 4 plus 1 is 5. 4 minus 1 is 3. Negative 1 to the 5 turns out to be negative 1. 0.1 to the 3 is 0.001. This gives you negative 0.999. And the last thing we need to find is the 8th term. So A8. So we're going to have negative 1 to the 8 plus 1 plus 0.1 to the 8 minus 1. So we have negative 1 to the power of 9, 0.1 to the power of 7. The thing to mention, and this is one of the things going on in these, you'll notice that if we put negative 1 squared, we got positive 1. If we put negative 1 cubed, we got negative 1. Negative 1 to the 4th is positive 1. Negative 1 to the 5th is negative 1. There's actually a pattern that's going on there. Negative 1 to any even power will always be positive 1. Negative 1 to any odd power will always be negative 1. So negative 1 to the 9th turns out to be negative 1. 0.1 to the 7th is 0, 0, 0, 0, 0, 0, 0, 1. 7 zeros and then a 1. That gives you negative 0.999999. 9. 7 nines. That's the 8th term in this sequence. Okay, so I'm going to leave it off here for today. I was hoping to get to the next topic in Chapter 9. It's okay that I didn't. I should still have time to go through all of this on Thursday's class. I may not have as much time for review on Thursday's class as I'd hoped, but what else was I going to say? Oh, yeah, group problem. That's what I was going to say. So yeah, again, for the rest of class today, for the next 10 minutes, you can work on today's group problem, which is this. It is a system of equations that I want you to solve. Oh, that was this. So if you can pull out some paper and try to solve that system of equations, with getting help from the folks in your group next to you or whatever, please put up your hand if you need any help with any of this. Yeah. Or if you, and I will go over the solutions in about 10 minutes. Oh, I'm just realizing that I saw some people squinting at this. I'm going to rewrite that line because it had gotten really small as I reached the edge of the board. I was doing that like, I don't know if you've ever seen that thing where it says like plan ahead and the like ahead goes down. Anyways. 3, 4, 5, 6, 1. There we go. Oh, did I? No, I did give out the handout. These are the old handouts from other class, yeah, but not last class as well. Uh-oh. Should I? Oh no, here they are. I also have some money's point cards here if anyone has anything they want me to go over at the beginning of next class. Oh. Did I? I just want to mention the answers to these ones are ugly numbers. They're not, yeah. The answers to this are fractions, and they're not nice fractions, like 1/2 or 2/3. They are actually, yeah. Oh, something happening downstairs in the stairwell. It's like, where's that noise coming from? Anyone have any solutions that we can check? Any questions about this? Yes.
I think these can reduce. It should be 30, like, we're talking about this, like, yeah. Otherwise, yeah, oh, yes, yeah, sorry, it doesn't say, so this is, yes. Yeah, and same thing with this one. 2 by 12, 1 by 3. Sorry, I'm just gonna.
Yes, yes, that's right. Yeah, sorry, I was confusing with one of the other ends.
Yes, exactly. Yeah.
Yes. 55. Perfect. Yes.
Wait, just really one here. Break that in there.
Oh.
I'm not sure. So I redo it.
Which method do you use to?
I thought I remembered an older version
Multiply
they changed.
2/3 by 2 becomes 4/3, not 4/6.
Oh, look at that.
Yeah.
Which is, if it was an exam question, I would have given you one that you did. Because it gives you nice answers.
Oh, yeah.
Exactly. Like I was going to say, is yeah. This is one of these, this is an example of a question which is in the book, which is more fussy than anything I would give on the exam. On the exam, I'm going to give things that have nice answers. So I'm just going to go over how I would solve this. I saw a whole bunch of people who got the right answers, and a bunch of them probably did something differently than I did. But what I'm going to do first, I'm going to multiply this whole thing by 10 to get rid of all these denominators. Because then I don't have any fractions anymore, and that'll make it easy to work with. So I multiply the whole thing by 10. So 1/2 times 10 is going to be 5. The 1/5 times 10 is going to be 2. And 3/2 times 10 is going to be 15. And the second one, I'm going to multiply by 12. And again, I'm just going to get rid of all those denominators. 2/3 of 12 is, 1/3 of 12 is 4, so it's 8. 1/4 of 12 is 3. And 5. And then I'm going to try to make these two guys cancel. So I'm going to multiply the first one by 3 and the second one by 2. So here times 3 times 2. So it'll be 15t minus 6v equals 45. And 16t plus 6v equals 15. And then if I add those two things together, 15t plus 16t is 31. 45 plus 10, there we go. 5 times 2 is 10, is 55. So t is going to be 55 over 31. And if you want to find what v is, I'm going to plug it into, let's say, the first one. So 5 times 55 over 31 minus 2v equals 15. boy. 5 times 55 is 275 over 31, minus 2v. 15 is 465 over 31. Negative 2v is 190 over 31. So v is going to be negative 95 over 31. So again, they're ugly numbers. If I was going to give you something with fractions on the exam, it would not have ugly S's like that. Yes?
So I've seen the times kind of textbook, right?
Yeah.
And, so I'm wondering if it's okay to kind of manipulate the equation right before being like, are we okay to manipulate the equations however we want, as long as we haven't put them together?
Yes. And actually, you're allowed to manipulate the equations however you want. You're always allowed to manipulate the equations however you want, period. As long as it's something you're allowed to do to an equation. So for example, you could even square both sides if you really wanted to. It wouldn't be useful, because if you squared this thing, you'd spoil and it would get really ugly. But you are even allowed to do that. So, yeah.
Okay.
Yeah. But thank you for asking that, because I definitely didn't explicitly say that you're allowed to do all, yeah.
Right. I mean, it should be pretty.
You're allowed to do anything you're allowed to do when solving equations.
Yeah.
That's, I guess, the other way of saying it. Like, there's, yeah.
Yeah, just really get you with my math skills.
Yeah.
Like,
Yeah, I got other answers, but like.
But you can get to submit them? Yeah.
To just like.
See the sun usually?
Yeah. Do you want me to give you an extension until tonight?
Yeah.
Yeah.
I'm surprised.
Okay.
Did you watch the email?
I'm going to do that
I
now.
watched some of it.
Yeah, I sent you a.
Did you send me an email?
No.
Okay.
I didn't actually see that.
I don't
heard
always
about it.
check that, so that's
But
the reason why I didn't get it. So I'm just going to do it now.
Scotland,
Yeah.
which is basically.
Just before the class.
Yeah.
My
kind of
Wi-Fi
exciting, like-
at home.
Oh, no, I watched that.
It's not.
Yeah.
Yeah, I was just kind of watching it. I wasn't really thinking. Like, I was watching it, but I wasn't like. After they scored the first goal, I was like,
Oh, or less. Yeah, they score one, so it's going to be more first.
So what's your last name? There we go. Okay.
You're talking like the Bruins goalies, like, they couldn't even get shots on net.
I know.
So tonight is okay?
Yeah, because I already.
Yeah, you've already got
Yeah,
that.
got all the answers, but.
I mean, yeah, they blocked a lot of shots and whatnot, but I'm pretty sure you're a good enough team that.
Thank you
Okay,
so much.
there you go. Yes.
I just have a question regarding the email I sent you. Did you get it?
The
I
one-
sent it like 4 or 5 hours ago.
I don't think I did.
Okay, I was just saying that I was checking through my group, like, 'cause I was wondering why my grades a little low. I was checking through my thing, and apparently, according to you, I haven't handed in my first assignment or my fourth assignment, and I.
Did you get emails back from, did you send them by email?
Hmm?
Did you send them by email?
Yeah, all of them have been sent by email.
Did you get an email back from me out of those cases?
Well, the fourth one, there's probably a reason that you haven't responded, because I just sent it to you, like, a couple of days ago.
Yes.
But the first one,
Yes, I haven't marked the fourth one yet, yeah.
the first one I handed in, but I don't seem to have any record of the
It will
email.
probably happen, and this is sometimes the UFB server loses emails.
Yeah.
So just forward me your original email you sent to me, and I'll mark it.
Will do.
Because as long as it has a date on it, then as long as before the due date, then I'll mark it. So, perfect. Yeah, exactly. Yes.
Check my smart. And was there a handout last Friday, like a little outline?
Yes, it's in my office.
Oh.
If you want an extra copy, or else it's on the course webpage.
Oh,
Whatever you prefer to.
Print it off.
Yeah, yeah. Yeah, that was 8.1, 8.2 handout, is what it would be called.
Okay.
Yeah. Sorry, which, you wanted to check the,
Mark.
yes. Let me, I just closed it. That's silly of me. Anyways, I totally had ours already signed in
No worries. And the written assignment is due
on Friday.
on Friday.
Yeah.
Oh, good.
Yeah, I figured that people would have more stuff happening this week, so I wanted to, like, do it the last day I'm going to be on campus for 2
Yeah.
weeks. So, yeah.
Okay, then.
So, let's see. Does it give you the? Oh, it doesn't give you. Yeah, it doesn't. Okay, never mind.
I'm going to have to go, now, okay, so you've got a B minus right now.
Okay.
Yeah. I don't know if that's, is this going to, yeah, it just gives you this thing, which is not, anyways, the view is that you can see your grades not at the best, because it doesn't tell you the mutations and all this with this view. So, yeah.
Okay.
Anyways, yeah.
B minus.
B minus, yeah. Anyways, and you can just look that up on, I think it'll give you a bit more information if you actually sign into WebAssign yourself.
Oh, okay.
And take a look at it. I think it gives you a bit more, because I was going to say, there's no, like, yeah.
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 Alright, cool. Great. Thank you.
You're welcome.
For this, this degree is written this over 90 degree.
Yes.
Yes.
Oh,
Yeah.
did I draw the picture wrong? Yes, yes, I totally draw the picture wrong. Yes, she should be down here. Okay. Yes, you're right. Let me draw you a new picture. Because you're right, with those numbers, so here are the two mountains. There's the distance between them. There we go. That's how the picture should look. Because you're right. 9 degrees would be here.
Okay. And as to this question, no, not use a lot of the signs and just use this. Okay.
As long as it gives you the right answers, then yes. Yeah, as long as it all works, then yes, that's definitely allowed. Yeah. But the only thing to keep in mind is because the picture was wrong, it might not work. Because it's going to have, yeah.
Because it,
So check if it does match the.
I think it's wrong because you know this is line, and use this line, and also this
Yeah.
this degree and
Yeah.
like this.
So as long as you like, as this question, how did you get this?
And I use
This-
this degree because this you know this is.
But yeah. How did you get? Yeah, that's the question. How did you get this?
And I use this line. This equal.
Oh.
So I got this is 50.
Okay, yeah. That angle is 50 degrees. But then what law did you use to find this side? Because the key thing is if you did it by drawing a horizontal line and doing it that way, that won't work.
Okay.
You see what I'm saying? Yeah. Yeah. So just check your calculations to make sure they still work if the picture looks like this. Yeah.
等下我忙事，我顶老师。他已经讲出来。